But here I cannot see.
Prasad, okay? Yeah. Prasad already started. You can introduce her. Let it things go.
Okay, fine. Let me just okay, I'll close this WhatsApp.
I will back after 20 minutes. I have one more meeting. I'll go and come back.
Okay, fine.
Okay, right.
I will just actually introduce and then we can start actually. It is connected to the YouTube, no? Yeah, YouTube.
It is connected. See, from Ramya's side, what I could see that some gray box is appearing on the screen.
Okay.
I don't know why it is appearing. Randomly it is appearing it.
Okay.
Could you see that or you are not seeing?
No, I cannot see that actually. Yes, there's a gray one coming. Yes, that is right.
Yeah, some gray color box is coming. Bigger one it is coming.
Right. Okay, I think then we can start now. Yeah.
Yeah, please. Go.
Okay. So Remya, am I audible?
Yes, sir.
Okay. So good evening to all the esteemed members of the Ocean Society of India, ladies and gentlemen. And we know that the Ocean Society of India conducts invited talk, which is a part of the OSA webinar once in every month. And this talk is arranged from eminent scientists, engineers, academic professionals working in the broad areas of atmospheric and oceanic sciences, ocean engineering and technology, and allied areas. And this webinar series is mainly targeted for students, researchers, scientists, engineers, and working professionals in the field of atmospheric and oceanic sciences, ocean engineering and technology, and allied disciplines, with a motive to impart and improve the knowledge benefiting the OSA community. So I earnestly request all the members to actively participate and get involved in all the lectures under the OSA webinar series that is held once in every month. So on behalf of the Ocean Society of India, it is my proud privilege today to welcome Dr. P.G. Remya, scientist of INCOIS, who will be delivering a talk on the topic Indian Ocean surface waves, research to service. So I'd like to give a brief background of Dr. Remya. So Remya actually has done her bachelor's in physics from Kannur University, Kerala, during 2001 to 2004, and completed her master's in physics from MG University, Kottayam, during 2004 to 2006, and PhD in physics from Gujarat University, Ahmedabad. And the research work was carried out at the Space Application Center, ISRO, Ahmedabad, during the period 2008 to 2012. She joined as a junior research fellow at Space Application Center in 2012 and as a scientist at INCOIS in 2013 and presently continuing at INCOIS. She has received the Young Scientist Award from the Telangana Academy of Sciences in the year 2018 and Associate Fellow of Telangana Academy of Science in 2020. And Dr. Remya is also PhD guide of QFOS Kerala, and she's a reviewer of many journals like Ocean Engineering, JGR Oceans, Climate Dynamics, Ocean Modeling, Operational Oceanography, The Dynamics of Atmosphere and Ocean, the Journal of Earth Systems Science, and the Indian Journal of Remote Sensing. Hello. Yeah. No, I'm in a meeting right now. Maybe you can call after 1 hour. Yeah. Okay. And she is also a lifetime member of the Indian Meteorological Society. And regarding the work experience of Dr. Remya, she works in the Applied Ocean Research Group at INCOIS, and that includes research on ocean wave modeling, operational wave forecasting, data assimilation, wave climate studies, wave-induced coastal erosion and inundation, handling of in-situ observations and remote sensing applications. And during her career at Ahmedabad Space Application Center, she has focused on the utilization of the satellite data for wave modeling applications. And At INCOIS, actually, she is setting up a global wave forecasting system using the WaveWatch 3 model. And this setup provides about 10 days of global wave forecast on a daily basis. And the wave forecast from the system is widely used by the fisherman community and the coastal population. The Maritime Board, Indian Navy, the Indian Coast Guard, the shipping sector, energy sector, oil and offshore exploration, and the port authorities. And she has done actually very seminal work on these ocean waves. And in particular, she has developed a forecasting system for the Kallakadal events, which is the most outstanding and innovative type of work that was carried out. And as we know that Kallakadal is a flash flood, the event that occurs during the pre-monsoon time without any precursors or any kind of local weather changes to warn the coastal population, which can cause major societal problems along the Indian coast. So Dr. Remya and her group has identified the link between the North Indian Ocean high swell events and the meteorological conditions in the Southern Ocean. That proves the Kallakadal events can be predicted almost 2 to 3 days in advance with proper monitoring of the meteorological conditions in the Southern Ocean. So based on this finding, a wave surge forecasting system has been set up at INCOIS, and the warnings of Kallakadal events are now being issued to the coastal community. At INCOIS, actually, Dr. Remya works on the ocean state forecast, concentrating mainly on the wave-related issues in the observations and the forecast. She also looks into the implementation of the data assimilation system that assimilates the observed wave heights of 3 satellite altimeters and the buoy wave data in the operational setup of WaveWatch 3 to provide an improved wave forecast to the community. She is also looking into the wave climate in the Indian Ocean region under different climate changing scenarios. The impact of various annual and the intra-annual variability on the Indian Ocean surface waves has been studied. And she is also interested in looking into the freak waves, which is dangerous waves actually that happens in the open ocean. And the group has also attempted to evaluate its occurrence in the Indian Ocean and to come out with a forecasting system. And Dr. Remya has been identified as a point of contact for extreme waves and erosion in the Deep Ocean Mission Climate Change Advisory Service. The influence of the Southern Ocean sea ice on the Indian Ocean swells was studied under this project, and it has showed significant impacts on the swells for the first time in the literature. And various wave climate analysis are in progress, which is also carried out as a part of this project. And she's also addressing some of the vital issues of coastal erosion, inundation along selected beaches in the Indian coast, which is very relevant in the climate change scenario. So very recently, actually, Dr. Remya has also, I think, published a very good paper that has come out in scientific reports, in which actually she has addressed the problem of the coastal inundation that the Chellanam coast in Kerala has been experiencing. And it's a very interesting work actually that has come out for the first time, in which the role of infragravity waves, as well as how the wave setup actually can, the higher wave setup that is encountered near the coast actually can lead to these flooding scenarios. So this is a brief profile of Dr. Remya. She is also very actively involved in guiding young researchers and students. She has published about 27 research articles in peer-reviewed journals and has guided 4 students for their MSc dissertation. And presently, there are 2 students who are doing their PhD under the guidance of Dr. Remya from QFOS, Kerala. So with this brief introduction, it is my proud privilege to kindly invite our eminent speaker, Dr. PG Remya, to deliver the talk. It's also requested that the questions and answers can be attended after completing the talk, and it can be messaged for the speaker in the chat box. Thank you very much. Dr. Remya, yeah, over to you.
Thank you, sir. Thank you for your nice words. Good evening, everyone. Today, I'll be talking about Indian Ocean surface waves. I work for INCOIS. INCOIS is the National Agency for Ocean State Forecasting. So so the development of a forecast system or the enhancement of forecast, that is a primary focus of all my wave related research. And today's title, Researcher Service, makes this clear.
Okay.
Here is the overview of today's talk. I'll begin my talk by pointing out the importance of wave forecasting. Then I'll give you a quick overview of wave forecasting system at INCOIS. Then with the example of Kadal forecast system, I'll try to illustrate how the research leads to the development of a forecast system. And in the last few slides, I'll try to connect waves with the climate change. Sorry.
Yes, the slide is in here.
Okay. So ocean surface waves or the ocean waves are the most observable aspect of any ocean. The oscillatory motions on the ocean surface are the combinations of different types of waves. And these waves are primarily classified based on their generation or restoration mechanism. So here I'm showing one diagram in which the waves are classified based on its wave period. So you can see it starts from the capillary waves, which is having a period around 0.1 second, and it goes up to the ordinary tidal waves, which is having a period of 12 to 24 hours. Okay, this is one of the famous diagram by Monk, generated by Monk in 1950. So in today's talk, I will be solely concentrating on this part of the classification, that is ordinary gravity waves, which is having a period of 1 second to 30 seconds. And these waves are generated by wind and restoring forces, gravity. So in this slide, I want to introduce some of the fundamentals for those who are not familiar with this wave research. So we are talking about wind generated waves. So there are mainly three factors affect the wave growth. Those are wind speed, pitch, and the duration. So pitch is the distance over which the wind blows, and duration says us how long the wind affects that distance. So this particular animation, the marked portion shows the pitch, and this animation will give you a better understanding of the idea of pitch. Sir, my slides are moving, right? Okay, there are two different types of wind-generated waves.
Yes, the slides are moving. Yeah.
Okay. There are two different. Sorry. There are two different types of wind-generated waves: wind C and swell. Wind C referred to short period waves that are in the generation area. You can see this one photograph. A wind sea dominated ocean looks like this. It will be chaotic and irregular waves are seen. So these are short period waves in the generation area. Once the wave move out of its generation area, we call it a swell. Those are long period waves and regular waves. So a swell dominated ocean state will look like this. So we all have seen waves from ripples to the large waves breaking at the beaches. So what is the importance of wave forecasting? Because this wind-generated ocean waves affect almost all the marine operations. For example, the cyclone-generated high waves can be deadly to fishermen who venture into the sea for their livelihood. So they want accurate wave forecasting for ensuring their safety. Similarly, the Disaster Management Authority, they need accurate wave information for the protection of the property and life of coastal population. And these wind-generated waves exert huge force on structures. So almost all the engineering application also requires the prior information of wave. So in short, you can see almost all the marine applications, starting from fishing, navigation, coastal infrastructure development, marine engineering applications, and the coastal population, all are hugely depending on this wave forecast. And from the ocean observation, like a wave observation, one can deduce the past and the present wave conditions. But for the future or for predicting the wave, we need a numerical model. A numerical model is nothing but it's a mathematical equation. So in a wave model, it takes three main processes. That is, the first one is wave generation by wind, and the second is wave propagation, and the third is wave dissipation. So when you put all these three processes together in the form of an equation, that forms your wave model. So what are the inputs to this wave model? You can give bathymetry, and wind is the generating force. So bathymetry and winds, if you give to the wave model, you are going to get the spectral information. So here I'll give you the concept of spectrum. So spectrum is nothing but it says us how the wave energy is distributed over different frequencies and over different directions. Here you can see I'm showing you one sample two-dimensional wave spectrum. This is for the location Hawaii, and like this wave spectrum for the time 18 UTC of 11th January 2007. And in this two-dimensional spectrum, this circle shows frequency. It's in the midpoint, it is 0, then 0.1, 0.2, and 0.3. The line shows this directions. Here it will be 0, 90, 180, and 270. 0 represents north, east, south, and west. And the color represents energy. So how will you interpret the spectrum? So here you can see in the lower frequency part, that is less than 0.1 hertz, you can see a energy patch. So when a low frequency energy patch means, like a low frequency means it's higher period, so that represents a swell system. So similarly, here you can see another low frequency energy patch that represents another swell system. And here you can see in this higher frequency another energy patch that represents wind sea. So at 18 UTC, 11th January, this Hawaii location was experiencing two different swell systems, one from northwest and another from northeast, and a wind sea from west. So this is how we interpret the wave spectrum. But this wave spectrum, two-dimensional wave spectrum in each and every grid point of your model is a huge information. You cannot handle it. So we always go for reduced output. That is the mean wave parameter, maps of mean wave parameters. So here you can see I have written significant wave height, mean wave period, peak wave period, and mean wave direction. Using this, we are going to like a forecast. We are going to give the forecast. So significant wave height, by definition, it is the average of 30% of the highest waves in a wave record, or you can say it is equivalent to the visual estimate of wave height. And peak wave period, here you can see I've shown one-dimensional spectrum. This is nothing but the frequency integrated one-dimensional spectrum that we extracted from this two-dimensional spectrum. So here, this one-dimensional spectrum tells us how the energy is distributed over different frequencies. And the peak frequency, you can see the dominant energy is coming around 0.056. TP is nothing but 1 by FP, where the dominant energy is located. And mean wave direction tells us the coming from direction of the wave. So in this slide, I'll give you a quick overview of INCOIS wave forecasting system. At INCOIS, we use wave-voice 3 model for the operational wave forecasting, and we use a multi-grid system, a 1 degree global grid, 0.5 degree Indian Ocean grid, and 0.25 degree North Indian Ocean grid, and a 4 kilometer coastal grid. And we use the latest version of WaveOS3, that is 6.07. And source time we use SD4. This source time we fixed after a sensitivity experiment. And bathymetry is E top 1. Spectral observation we use 29 frequencies and 36 directions. And this particular setup provides 10 days wave forecast in advance using two different wind forcings, NCMWF and ECMWF. And you know that data assimilation is a proven technique for improving your data, improving your forecast. So we assimilate all the available significant wave height information from in the Indian Ocean, that is from wave-guided buoy, moored buoy, and altimeter. We assimilate all the information into our operational setup and provide the forecast. So this animation here, it shows a sample of global wave forecast. Here you can see the color represents significant wave height and the vector represents mean wave direction. You can see the propagation from southern Indian Ocean to the northern Indian Ocean here. And wave forecasts are available for global, regional, and coastal scale. We also provide location specific forecast, and also customized user products also we provide. If you want to see the forecast, you can visit this website, this portal. Sorry. And these are our users. You can see fishermen, navigators, ports and harbors, Indian Navy, Indian Coast Guard, maritime industries, disaster management agencies, coastal population researchers, ecologists and environmentalists, policymakers and academia are using this wave forecast. This long list of users itself tells us like why the wave forecasting is very important. So, to set up a wave forecasting system for a particular region, one should know the wave characteristics of that region. So here I'm showing two graphs. You take any one point in the Bay of Bengal and one point in the Arabian Sea and just plot the significant wave height for 1 year. You are going to get a graph similar to this. You always see in the pre-monsoon very low wave heights, and in the monsoon very high wave heights of the order 4 to 6 meter, and again in the post-monsoon the waves start decreasing. So, but in sometimes in the pre-monsoon and post-monsoon you will see some high wave heights event. That is mostly due to Southern Ocean swell dominance. And in the monsoon, I don't have to tell you anything about monsoon because the monsoon high winds creates monsoon high waves that everybody knows. And then sometimes in the pre-monsoon and post-monsoon, we'll see again very high waves of the order, sometimes of the order of 9 to 10 meter. That is mostly cyclone generated. So as far as the Indian Ocean wave forecasting is concerned, we have to worry about three conditions. Those are Southern Ocean swells, monsoon, and the cyclone. So once you complete a wave forecasting setup, a thorough validation of forecast under all these conditions are very important. So here I'm showing you some sample validation, some validation graphs. So here the first graph, the first graph, that is a comparison of model forecast, comparison of forecast with the deep ocean observation for 1 year. You can see the model is agreeing, the forecast is agreeing very well with the observation. This is for a deep ocean location in Arabian Sea. And here I'm showing at Ratnagiri location, this is a coastal location. We have used wave for buoy data for the validation. Here also you can see how good is the forecast, how good it is agreeing with the observation. So these two proves our reliability of the forecast for the North Indian Ocean. All our in situ observations are located in the North Indian Ocean. So for the validation of the entire Indian Ocean domain, we have to depend on satellite altimeter data. So here in the spatial plot, I'm showing you the along track validation of significant wave height. You can see entire Indian Ocean, we are getting good agreement with the observation. So in this graph, this shows the comparison of spectral energy at Indica location. During the Rono cyclone case, here also you can see the model is agreeing very well with the observation. So this is how we establish the reliability of our forecasting system, and this validation exercise are published now in Journal of Operational Oceanography. This paper, this article is the one of the reference paper for our Indian Ocean wave forecasting system at INCOIS. These are the wave observations available in the Indian Ocean. So we have wave radar buoys along the Indian coast. Each coastal states we have one buoy. These buoys are from INCOIS Warman network. And we have mood buoy in the deep ocean, that is from NIOT network. And we have presently 3 satellite data available. Those are Satellittica, JSON3, and Sentinel-1. So we use all these observation for validation and assimilation in our operational setup. And I think INCOIS is the only agency which provide real-time validation of its forecast in the website. So if you go and see our website, you can see the validation of our forecast with all these mode buoys and wave radar buoys on a day-to-day basis. So as I told earlier, data assimilation is a proven method to improve your forecast. So in the operational setup, now we are assimilating all the available significant wave height observation from the observation of Indian Ocean, and we are getting 10 to 15% improvement in our forecast in the first 72 hours. You know that Indian Ocean is a swell-dominated ocean. So because of the longer memory of swells, the assimilation works really well for the Indian Ocean. And this like validation and the details of the data assimilation system is published now in Ocean Engineering. You can refer Siemens Data 2021 for more details of the data assimilation system. So this article also works as a reference for our Indian Ocean wave forecasting system at INCOIS. Okay. So with this one example, I'll try to tell you how the research leads to the development of forecasting system. We are talking about the wind-generated waves, and this wind-generated waves can travel thousands of kilometers and reach far distant coastal destinations as well. And many studies in the Indian Ocean showed that this Southern Ocean swells, the swells coming from Southern Ocean, is a which can influence the North Indian Ocean. Also, it is identified as one of the major component of North Indian Ocean wave climate. And these swells impact our coastal regions and the Indian wave climate in different ways, and one of them is the Kallakadal. So Kallakadal is a flash flooding event without any precursors or any kind of local wind activity to give advance warning to the coastal population. So the major Kallakadal event happened in May 2005, just after the Indian Ocean tsunami, December 2004 Indian Ocean tsunami. The southwest coast of India, especially the Kerala coast, was experiencing severe flooding. So this was just after tsunami. People became panicked, and it got a lot of media attention. And from there on, the people started noticing this Kallakadal event. And in 2009, Kujinatal has reported this special case of coastal flooding. And they reported that Kallakadal is happening in pre-monsoon season, and they identify the presence of long period swells during the Kallakadal time. And Kallakadal is a local language term. It's a term. It's in Malayalam. Kallan means thief. Kadal means sea. So the meaning is sea is coming like it comes like a thief and stealing the properties. So this term Kallakadal is formally accepted by UNESCO in 2012 for swell-induced or wave-induced flooding. Then still it remained as a forecast issue because there were there were any precursors or any kind of local wind activity was not noticed to give advanced warning to the coastal population. And INCOIS started addressing the issue. So as an initial step, we gathered all the available observation during 2005 because the major Kallakadal event happened during May 17 to 21, 2005. And we got 4 shallow water observations and 1 deep water observation during 2005 to analyze the event. So this is DS5 is of Visakhapatnam, SW6 of Ennore, SW5 is of Tuticorin, SW4 represents of Mangalore, and SW3 of Goa. So we didn't get any observation from Kerala coast. So we took SW4 as a representative location. And in the work of Corin et al. 2010, they have clearly stated the presence of long period swells. So we started from there. Actually, then we created a criteria to extract the high swell event from the observation. So we use the criteria long period swells greater than 14 seconds that are having a moderate height that is greater than 0.4 meter and lasting for at least half a day. 12 hours. So we extracted all the high swell events, and you can see here 6 such events in the SW4 location. SW3 also having 6 such events. SW5 that is of Tuticorin didn't have all the 6. It has only 5. And SW6, which comes in the shadow region of Sri Lanka. So only 1 event was detected in that. And here at SDS5 location, spectrum data was available. So we plotted only low frequency part of the spectrum that represents swell. Here you can see the swell systems, low frequency energies in the low frequency part. So that represents the swell systems. So from this one analysis, we clearly we confirmed the presence of high period swells in all locations. Now, you can see in the all graphs, the major swell event 17 to 21 is appearing in all graphs. So, we started with the May 17 to 21 event. Here, you can see we took Mangalore as a representative location, and we plotted the 17 to 21 event here. Red color represents significant wave height. Green represents swell wave height. Peak wave period is blue dots. And this plot you see, it just showed a gradual increase from 0.7 to 1.2 meter during the period 17 to 21 May. And if you see the green time series here, that represents a significant swell height. You can see the similar increase is seen in the swell height. Significant wave height is a combination of swell and wind sea. So any increase in the significant swell height will cause an increase in the significant wave height. So on 17th May, we observed 22nd wave that hit the coast on 17 May, followed by short period waves. And this remained around like 14 seconds for some few hours. Then after that, on 20th May, again, one high period wave hit the location, followed by short period waves. So here I'll explain you the concept of dispersion. So waves generated in the fetch area undergo nonlinear interactions and leave the fetch as swells. So once it leaves the fetch, the high period waves travel faster compared to the short period waves, and the longer period waves reach the coastal destination, followed by shorter period waves. And you are seeing the same thing here. The high period waves which hit the coastal location, we call it as forerunners, and it is followed by short period waves. So from this graph, we can clearly state these swells are from two different origin, or these are two different swell systems. So now what we have to check. Now we clearly identified the presence of two swell system during the period 17 to 21 May. Now we have to find the origin of this swell system. So in the pre-monsoon, the winds are weak in the North Indian Ocean. So definitely we can assume that these waves must have come from the Southern Ocean. The Southern Ocean only that kind of strong winds and large fish is available. So to confirm the origin of these swells, we had done some model experiment. We had done two different simulations. In the first simulation, we had given winds in the full Indian Ocean, and in the second simulation, we used winds only in the 40 to 60 Southern Ocean band, and we allowed the swells to freely propagate into the North Indian Ocean. So if you compare, when you compare the spectrum, what we got is in both the cases, we could see the low frequency swells. That means these swells are from the Southern Oceans. So this experiment confirmed the origin as Southern Ocean. Then we started analyzing the meteorological conditions in the Southern Indian Ocean. For that, we have used surface wind fields from Quick-Scat Spectrometer. And here you can see on 14 May, we could identify a large patch of strong wind speed. And again, on 16th May, we identified another patch of strong wind speed. So, what caused this very strong winds? And using the wave-induced model runs, we identified the swells that propagated from these two patches. So, what caused this very high wind at this region? So, further analysis revealed the presence of cutoff low in these regions. Cutoff low corresponds to a closed low geopotential height in the upper troposphere that has become completely detached from basic westerly jets and usually are being advected equatorward of the mid-latitude westerlies. So what happens when the cutoff low is formed in the path of westerly jet? So the cutoff low, it blocks the normal course of westerly and it leads to the stagnation of weather patterns and strong surface winds over a large area. So the cutoff flow systems, the one specialty of these cutoff flow systems are it is quasi-stationary in nature. And hence, this slow-moving system provides strong wind speed, long duration, and large fridge. These three conditions are essential for high wave growth. So it provides all the essential condition for wave growth. And at the generation area, we have seen almost 12 to 15 meter significant wave height. And the intense wind at this location, from this figure, you can see it is oriented towards north. So this orientation of the strong winds towards north caused the swells to travel to north. It caused the wave propagation towards North Indian Ocean. So in short, the intense wind associated with the cutoff flows in the Southern Ocean triggered the swell generation and it propagated towards North Indian Ocean. So in this slide, I am showing the various stages of cutoff flow. There are 4 stages, a trough formation, then a tear-off stage, then the closed circulation becomes dominant, then a dissipation stage. So this first panel shows the schematic diagram and the second panel shows the real cutoff flow. So whatever you are seeing in the schematic diagram, that is clearly seen in the real COL. You can easily identify the real COL here and each stages. So now with all these analysis, we confirmed the cause as blocking of westerly winds by the cutoff flow as the reason for high wave generation in the Southern Ocean. And now you see the wave propagation from the Southern Ocean. The first set of swell waves hit the Indian coast around 16 May. and then followed by another swell system that hit the coast around 28th May. So this confirmed the May 17 to 21 event, the cause, we could identify the cause of May 17 to 21 event. But the first graph, which we generated by extracting the high swell events, showed 6 such events. So whether these cutoff flows are present in all the 6 events, that was our next question. So we checked the Southern Ocean conditions for all the 6 events, and we could identify the presence of cutoff flow in all the 6 events. And you can see the scatometer wind shows the high strong winds in the cutoff flow regions, and the wave propagation from the region towards North Indian Ocean. This table shows like the tropical cyclone we classify as cyclone, severe cyclone, super cyclone. In the similar way, we can classify this cutoff flow system also as weak, moderate, and strong based on the blocking intensity. So this table shows this shows the intensity of the cutoff flow, and you can see all the 6 events. The cutoff flow intensity of the cutoff flow was very strong. So the strong cutoff flows caused the swell propagation towards North Indian Ocean. The work of Kurin et al. And other reports was mentioning all these events are happening in the pre-monsoon season, and we wanted to check whether these events are happening only in the pre-monsoon. So in the shallow water location, the continuous observation was not available for 1 year. So we used TS5 location data for checking the low frequency swell occurrence. And you can see when we extracted the low frequency swells, we could get many such events. And using the criteria which I said earlier, we could extract 9 such events for 2005 year. And all the 9 events, we could identify the presence of cutoff flow, and the cutoff flow and the intensity of each was moderate to strong. So from this table, we concluded, so these are our conclusions. Origin of all high swell incidents were associated with this cutoff flow system in the Southern Ocean 3 to 6 days before the high wave activity in NEO. And these cutoff flows are of high intensity with PI values more than 3. Location, intensity, duration, and quasi-stationary nature of the cutoff flows determine the energy and period of the swell waves. And high swell events which are occurring without any signs in the local weather can be effectively monitored and forecasted at least 2 days in advance if the meteorological conditions of the Southern Oceans are properly monitored. So this results we published in GGR in 2016. And based on the study, here I forgot to say one thing. Because all the reports were saying the Kallakadal events are happening in pre-monsoon. Why? Because in the North Indian Ocean, very low wave heights are seen mostly in the pre-monsoon season. So the swell domination, or when the Kallakadal event happens, these are clearly noticed during pre-monsoon. But since in the monsoon and other seasons, mostly the wave heights are high, so these events go unnoticed. That is one reason. And the second reason, the occurrence of cutoff flow systems in the Southern Ocean are more during March, April, May. So because of these 2 reasons, these events are appearing mostly in the pre-monsoon. Based on this study, we established the Kallakadal forecasting system at INCOIS. Here I'm showing one forecast. This animation shows the Southern Ocean wave propagation from Southern Ocean. The color represents peak wave period. You can see the waves are propagating from Southern Ocean, and it is directed towards Indian coast. And we have a wave radar buoy at Seychelles, and we use that buoy for tracking of the swell. Here you can see the low frequency, dominant energy in the low frequency part. And the corresponding cut-off flow in the Southern Ocean is represented, shown in this plot. And these are the various news reports for this particular event. You can see here, unexpected sea surge at Alapura coast, 27 fishing boats washed away. This was published in Indian Express on 2nd August 2016. So we could, INCOIS has issued timely wave surge alert for this particular event. Here you can see one photograph of high waves that is in Alt Dika, West Bengal. So this is another Kallakadal event happened during 21 to 24 April 2018. This was almost similar to the May 2005 event. This was a very strong event. And here you can see the swell propagation from Southern Ocean to North Indian Ocean. You can see here the cut-off flow is formed on 15th April 2018 near 59 South and 29 East. That is almost 9,000 kilometers away from our Indian coast. This is a very interesting thing because these swell waves are traveling like 9,000 to 10,000 kilometers. These waves are traveling and these are coming to our Indian coast and creating issues in our coastal areas. And this is really interesting. Also, this is very important. So from this we can understand it is very important to understand the nature of such swells. We have to do more research on these swells. And we have to understand the nature of these swells, especially in this climate change scenario. And here you can again see one newspaper report. The heading itself is coastal areas in Kerala battered by swell waves. Again, for tracking, we used Seychelles buoy, and we had issued timely warning for this event also. Here I'm showing one sample alert issued during 21 to 24 April 2018. Event type is alert, priority is high priority, and the message is like this. There's a possibility that sea will be rough near shore, and also the low-lying areas may experience surges intermittently during so and so hours due to the effect of high period swells. So when these waves enter into the shallow water, what will happen? These are high period swells. So when it enters into the shallow water, once it starts filling the bottom, the wave speed decreases, the wave velocity decreases, wave length decreases, wave height increases. I'm talking about the shoaling. So when the wave height increases and when it that leads to the wave breaking. Once the wave breaks, it creates a wave setup in the nearshore region. So when these wave setup combine with high tide, that causes the coastal flooding in the nearshore regions. But this will happen only when the wave setup is combined with high tide. During the low tide, these events will create rough sea condition in the nearshore areas. So in our forecast advisory, we are giving two types of warning. One is rough sea alert, one is wave surge alert. When the event is combined with high tide, we are issuing the surge alert. But in our forecast, now we are not providing the inundation extent. Now we have experimentally set up a system that is a combination of wave-3 ATSEC swan coupled model system that we use to predict, that we are now using to predict the inundation extent. That is now experiment. We will be making it operational soon. So this is how we developed the Kallakadal forecasting system. I hope now it is very clear that how the research is leading to the development of a forecasting system. So in this slide, is also tells about coastal flooding, but this time it is due to cyclone generated waves, cyclone generated high waves. Until recent past, the west coast of India was not experiencing any high waves due to cyclones. But from the occurrence of Oki onwards, the condition changed. During Oki time, India west coast of India affected by the Oki generated high waves, and many coastal regions experienced coastal flooding, erosion, and high wave activity. The same story repeated recently during Taute cyclone case that happened during May 2021. And one of the most affected state was Kerala. And in Kerala, the Chellanam coast that was severely affected by high waves and coastal inundation. So we are successful in predicting the cyclone generated high waves, but we don't have presently we don't have any operational system to predict wave induced coastal flooding. So what we tried a combination. This is an innovative approach. So we tried a combination of wave-3 and X-speech to study the coastal inundation during high waves. So we have given the wave output from our operational wave-3 model to X-beach along with the tide. And definitely we need bathymetry and topography data for the coastal inundation forecast. So we had given that also to X-beach. And we tried to simulate the coastal inundation during Taute cyclone period. And we have seen that coastal flooding at Chellanam happened during low tide condition, and the storm surge at the region was negligible. It was only 15 centimeter. So low tide and negligible storm surge. Then what caused the coastal flooding at this region? That was because of the effect of low frequency wave. That low frequency here I mean infragravity wave, which comes in the next band of wind generated waves. You can say the frequency will be coming around 0.04 hertz to 0.004 hertz. So that band we call frequent infragravity wave. So the presence of infragravity wave, we can see we have extracted the infragravity wave height here. You can see this infragravity wave along with the wave setup. You can see in the nearshore regions almost 0.7 meter wave setup. So a combined effect of these two caused inundation at Chellanam even during low tide condition. Here, this plot shows the model estimated or model simulated coastal inundation we overlaid on the Google Earth image. This is the Chellanam area. Here you can see marked 4 locations, A, B, C, D. This corresponds to this is the photograph. This is the ground truth. These photographs are taken during Taute period. You can match these 2 locations. So all the locations can see inundation. So we are able to predict the coastal inundation during Taute. We could predict the coastal inundation during Taute cyclone using a combination of Vivas-3 and X-speech model. We are successful in that. So the conclusion is the inundation of Chellanam emphasized the contribution of infragravity waves and wave setup on the overtopping of the waves, inundating the coastal regions that are often ignored in the operational framework of coastal inundation during cyclone conditions. When we hear cyclone and the coastal flooding, we always think about a high tide condition, a combined condition of high tide and storm surge. But this one example of Chellanam tells us the role of it tells us we cannot anymore ignore the role of cyclone generated high waves in the coastal flooding. So that is the one main important point this study gives us. So this is also published recently. This was published in scientific reports. So anybody wants to know more about this research, you can always refer Reddish et al. 2022 scientific reports paper. So the research part of this work is over. Now we are going to set up an operational system initially for Chellanam, and then we will extend the forecast system for other hotspots of Indian coast. So now I'll try to, in this slide, I'll try to connect these waves with climate change. Climate change, when we talk about climate change, the first things comes to our mind is the sea level rise. But sea level rise is not the only climate change that's going to affect our coastal areas. the warming planet changes wave climate also. We have seen many studies saying that the global wind patterns are changing due to warming. So definitely any change in the global wind pattern, that will reflect on the wave also. During recent past, IPCC working group recognized this wave as one of the 8 main major climate driver for coastal region. And when I say wave climate change, it's not about the wave height. It's not about the wave height changes, or it is not about the increase in the wave height. If you see the research papers, you can see only 5% of the world coasts are seeing an increase in the wave height, and 15% of the coasts are going to experience decrease in the wave height. Then what is mean by wave climate change? It is not about the height change. It is about the height change. It is about the period change, and it is about the direction change. So basically, it is about the characteristic change in the wave characteristics along the coastal regions. For example, in the recently we also started working on the Indonesian wave climate, and we have studied the impact of various climates modes on Indonesian surface waves. And what we have seen, if you take the climate modes in SAM and IOD, SAM has significant impact on the Indonesian swell conditions. You can see the work of Naiketal 2013 and the work of Singedan 2018. This both study shows the propagation of Southern Ocean swells more towards the Bay of Bengal. And Arabian Sea, it's not the propagation is more towards Bay of Bengal, and the Arabian Sea is not much affected. But in our study, we have seen during a positive SAM phase, the swell generation areas in the Indian Oceans are getting shifted. It is getting shifted towards the eastern side. So what will happen? So the swell from the Southern Ocean will be directed more towards the Arabian Sea. So now the Arabian Sea characteristics are it's a mixed state. Wind sea and young swells are present most of the time. So if there is in future, if there is an increasing SAM positive phase, then that will definitely direct the swell towards Arabian Sea. So the Arabian Sea wave characteristics changes. Our Indian coastal regions will be receiving more long period swells. So more long period swells means there is a chance of more coastal flooding events, then there is a chance of more coastal erosion. So in one of our study that we conducted in the Erida beach, close to Visakhapatnam, we are seeing the coastal erosion is more during the presence of swells. So this is the way that wave climate change going to affect our coastal regions, and this clearly shows that wave climate, understanding the Indian Ocean wave climate and its changes are very important. And under the Deep Ocean Mission, we are addressing this issue. Deep Ocean Mission, there are 6 verticals, and vertical 2 is representing ocean climate change advisory services. The broad objective of the mission is to facilitate climate change advisories for the societal and economical benefit of the Indian coastal regions. So under vertical 2, there are 5 components, and one of them is extreme waves and coastal erosion. So soon we will be developing the climate services for the Indian Ocean and Indian coastal areas. So in conclusion, what I want to say is the development of wave-induced inundation and erosion forecast system is needed at the present, as the extreme waves may cause the worst damage to the coast when it acts together with storm surges, heavy rains, and a rising sea level in the anticipated climate change scenario. We cannot ignore the role of waves in coastal flooding or in the coastal erosion. That is what I want to conclude. So thank you. Once again, I thank Ocean Society of India and Dr. Prasad Bhaskaran for giving me this wonderful opportunity to talk about Indian Ocean surface wave. If you have any queries related to the research work presented here, you can write to me. My email address is remya.pg@incois.gov.in. Thank you.
Thank you, Dr. Remya. It is a very interesting and a wonderful presentation.
Thank you, sir.
So you had actually covered right from the basics to the services that INCOIS is offering, the varied services that INCOIS is offering in context to the ocean waves. So your presentation started basically with the classification of ocean waves, in which you had actually given broad details about the short period and the long period, that is the wind seas and swells,
Yes,
and the importance of the wave forecasting, and also why these numerical wave models are employed for understanding the spatial and the temporal variability of ocean waves, in which you had elaborated more about the winds, then the wave model, then the full spectral wave forecast fields. Thereafter, you had actually touched upon the wave spectrum and the importance of the wave spectrum in context to the energy balance equation. You also covered the configuration of the WaveWatch 3 that is being used at INCOIS on the global scale, the regional, coastal, and the location-specific scales, and the characteristics of waves that we find in the Indian Ocean region. Then you have actually also touched upon the validation of this model results, that is the WaveWatch 3 regional wave forecast with the long track validation of the satellite data, in which you find a very good match between the WaveWatch 3, the current configuration of WaveWatch 3. And also on the data assimilation system that you have used, the JSON, Savell, Altica, and the Sentinel data for in which the data assimilation is basically made in the wave forecasting system, so that the overall quality of the results have improved. I think that's a very good step actually that has been taken, because now we need to find out the different techniques in which we can enhance the quality of the results. And I think the data assimilation has shown very promising results also in this field.
Yes.
Yeah. Hello. JLF is 31 and SRM is 35. Yeah. Yes, that is fine. Yeah. Okay. Thank you. Yes, then I think after that you had also talked about some of the major events, the colloidal events that the coast of Kerala has been facing since a long time. And I think the answer to that has been clearly brought out. Actually, how this cutoff flow actually, which is happening somewhere 9,000, 10,000 kilometers away from the Indian coast, basically the teleconnection between that and how the high swell activity that is happening and inundating the coastline. I think that has been very clearly brought out, and it's a very, very wonderful work actually that has come out.
Yes.
And the wave spectrum comparison also you have done with the low frequency swells in the Southern Ocean region and how it is related to the cutoff flow. And I think you have also taken this work one step ahead, in which you have classified this cutoff of the pre-monsoon period into the weak, moderate, and the strong events, and how they basically influence the coastal flooding in the Kerala coast. Then thereafter, you have also talked about the coastal flooding with some of the recent studies that has been carried out, in which the cyclone generated high waves has been simulated using the WaveWatch 3 and the XBridge model. And very interestingly, that you have also pointed out in one of the last, I think the last slide, where the SAM period, when you have a Southern Ocean annular mode with a positive phase, and how it basically shifts the wave system towards the eastern side, so that the Kerala coast also get a part of it. So that is very interesting actually. And finally, you have concluded your talk with the recent activities of the Deep Ocean mission and the way forward. I think that's really very good. So let me just go to the chat box and have a look actually, were there any questions that have been put? I think so far there are no questions which have come out. But I have just actually listed down about a couple of questions, which I would like to have a small discussion on that.
Yes, sir.
Okay. Because since it is a live this thing, there will be a lot of viewers actually who comes after the office hours also. There will be a lot of viewers in the after office time. So I've noted on my first question. You have mentioned about the cutoff flow,
Yes.
that happens, which is a meteorological phenomena that happens in the Southern Ocean region.
Mm.
And you say that about you have a lead time of about 2 to 3 days. Once a cutoff event happens in the Southern Ocean, then after a period of 2 to 3 days time, we can see its effect on the Indian coast, the southern part of India. Right.
Yes.
So my question here is that suppose let us say that you had already identified a cutoff flow that has happened today. Today, let us say that there is a cutoff flow that happened in the Southern Ocean, and if suppose you have a local wind system in the what you can say the North Indian Ocean, which is quite strong. So how do they react actually? Is it having any connection with the local wind system?
So your question is,
Uh,
when these swell waves arrive at the coast, do these two interact? Or
do this local wind system interact with these long swells that is coming to the coastline? Yeah.
I don't think it can interact
Okay. I think
because
yes.
these are long period.
Exactly. That
So
is what I was also guessing the same. Since these are actually long period waves, it hardly is affected by any wind system actually, because its wavelength is too long. And not only that, I think if you look into the profile of these swells, which are coming from very far away, the shapes of the swells doesn't permit actually in either breaks due to wave breaking, nor I think the wind can have any effect in enhancing it. I think maybe that actually requires a little bit. We need
one
to have,
possibility
yeah.
of generation of infragravity wave in the nearshore is one possibility that we haven't explored yet. That I think we will do it with the same combination of advisory and X-fish. We never tried that. Whether these wells, when it enters the nearshore, whether it can generate infragravity wave at the location.
Yeah, I think that is
So
a very
that
interesting thing that needs to be explored actually. Whether these swells are getting modified or something into the infragravity waves, and then how it is. Yeah. That is a very interesting topic to be looked into. So that is my first question. My second question is, you mentioned about this southern annular mode, the SAM event that happens in the Southern Ocean. So as of today, do we have any meteorological monitoring station at the Southern Ocean which can monitor the Southern Ocean cutoff frequency or the cutoff flow? We
no,
don't
sir.
have any monitoring. We don't
We
have
don't
any.
have.
I think that we need to build upon maybe in the future. There need to be a monitoring system, a robust monitoring system actually, so that this type of teleconnection events can be studied in detail. Yeah, I think so. So as of now, if I understand, actually we are only depending on the what you can say the global data, the atmospheric data, and then we are identifying the cutoff flow from that. Maybe I think yes, we need to have a monitoring station also in the Southern Ocean. I think that is an area where actually we don't have much of monitoring, which is really happening.
Yeah, we really have to focus on the extratropical areas. That is really required because the swells waves are affecting our Indian coastal regions.
Right,
So
right.
we have to focus our research on that extratropical areas.
Okay, but do we have any mood buoys in that region? Mood buoys which can measure wave heights?
No, sir. Actually, we were trying to deploy one mode buoy there, but like you know that furious
Yeah.
50s and the roaring 40s, we
Yeah,
can't.
it's extremely. The sea is very chaotic and it's very rough in that area. Absolutely
So
very rough.
that's why we
Right.
deployed 4 wave drifters to study the Southern Ocean Southern Ocean wave characteristics.
Right,
We
right.
deployed 4 wave drifters there recently. Under deep ocean mission, we are going to buy more wave drifters. Those are also like those will be deploying. We will be deploying those drifters also in the Southern Ocean. So I think with that we can at least study the wave characteristics of Southern
Right.
Ocean.
So I think this is my final question, the third question which I made. You mentioned about the southern annular mode, no, right? And how it basically can impact uh, the wave systems basically at some other location. Now, we had also conducted a study some time back, and what we found something interesting in that is when we identify the zone where you have this SAM, because SAM basically comes in the extratropical belt, which is covering a particular region. And we found actually very interesting that the SAM orientation is changing. That means the directionality of SAM is changing. But I'm just wondering actually whether this directionality change, what we are seeing, is it somehow connected with the positive and the negative phase of this, you mentioned, no, the positive SAM and the negative aspect of the SAM. Maybe it is having a connection, the orientation that we have seen. But there is a shift in the orientation that we have noticed.
That we did not address in our study.
Almost about 10 to 11 degrees. If you take the what you can say, the overall means, if I take a shape of the entire SAM, where the area or the area where the SAM is being affected, no, there is a change in the orientation that is being seen.
No, I'm not aware of that, so I'll look into that.
Okay. Yeah. That's fine. That I think we have done a study on that sometime, some 4-5 years back. Maybe I can share that paper with you also. You can just have a look into that. Yeah.
Yes, sir. Sure.
It is basically the dipole. I think the paper basically is something on. Let me see. I think I have a copy of that in my mobile. I can tell you the name of that. That is, yes. I can just tell you the name of that article. Yeah, that the article basically is the dipole behavior in the maximum significant wave height over the southern Indian Ocean. It basically talks about the shift in the orientation of this SAM, actually.
I'll go through that.
Yeah. I think this, but we have done that. If I remember rightly, we have not used the present data, but until 2010 or something we have used, 2010 or 2012. Beyond that, we have not looked into how the orientation has further changed. But there is a shift in the orientation that we have clearly seen. Yeah. So I think, Dr. Remya, it is a very interesting and a very important topic, at least in context to the climate change and the eroding coastlines that we are experiencing today. You have really covered actually how the science can be taken to service. I think this is the need of the hour, and I really appreciate the time and efforts that you have given for the seminar. And I'm very sure that the viewers actually will be much benefited, and it will surge the interest among the young people to take on this topic to the higher levels. So now let me have a look into the chat box if there are any further questions. That is, no, I think there are no questions that is being put by the viewers so far. Maybe they may be putting it in the YouTube after some time. So thank you very much, Dr. Remya. And on behalf of the Ocean Society of India, actually, again, thank you for your time and effort. And maybe the Chelanam topic that you have actually recently published in the scientific reports, I think we may need to have a discussion sometime in one of the local chapters of the Ocean Society of India. Like the Cochin chapter is quite active in this, and we had a talk about this Chelanam and this high wave events maybe some few months back. I think these results what you have got is really very interesting. Actually, I think this will create more interest among the people who are working in the Kerala coast. I think it's a new result actually we have come out with. Actually, it's very interesting.
Yeah, it's an innovative approach.
Right. I think we need to carry forward that also. Maybe you can also look for a forecasting system for this also.
We are planning to start.
Yeah, that's very good. Really appreciate that work. It's very good.
Yes, sir.
Thank you very much, Dr. Remya. Yeah, thank you.
Okay, thank you.